Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the buffer register and controlled buffer register. This topic is meant for MSc students of Physics and Electronics and also for BE and BTech students of EEE and ECE branches. The research scholars will also find this topic useful. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. Before I start dealing with the register, let me remind you that a register is nothing more than a group of flip-flops that work together as unit to store a binary information. Now what is a flip-flop? A flip-flop is another name for a bistable multivibrator, which means that it has two stable states, the 0 state and the 1 state. Since it can store 1 bit of information in its output can be either 0 or 1. It is used as the basic memory element in digital computers. Depending upon the circuit design, a flip-flop can be used to count binary numbers or store them in registers. It can also perform various logical operations and is the basic building block of shift registers used in multiplication. Okay? Since each flip-flop stores 1 bit of information, which can be either 0 or 1, the number of flip-flops required in a register is equal to the number of bits in the binary word. Registers find applications in a number of digital systems, including microprocessors, where they are used as memory elements. A counter is a special kind of register designed to count the number of clock pulses arriving at its input. Since the clock pulses occur at regular intervals, a counter can also be used as an instrument for measuring time and therefore the frequency. Okay? Now let us come to the buffer registers. What is a buffer register? Buffer registers. A buffer register is the simplest kind of a register. In figure 1, we have shown a 4-bit buffer register built with positive age-triggered D flip-flops. Now recall the truth table of positive age-triggered D flip-flop. When the positive edge of the clock pulse hits the D flip-flop, the input is transferred to the output of the flip-flop. All the flip-flops are driven by the same clock pulse, so that when the positive edge of the clock pulse arrives, the inputs of the flip-flops are transferred to their respective outputs, and the stored word becomes Q3, Q2, Q1, Q0 is X3, X2, X1, X0. So this is a D flip-flop. The symbol shows that this is positive edge triggering. This is the input to the flip-flop X3. This is connected here, so this is D3. So when the positive edge of the clock pulse hits the flip-flop, this D3 will be transferred to the output Q3 here. Okay? So Q3, so these all are identical. The same clock pulse is applied to all the D flip-flops. So whenever the positive edge of the clock pulse hits the D flip-flop, the inputs X3, X2, X1, X0 are transferred to the output Q3, Q2, Q1, Q0. Okay? At the same time, in symbolic notation, we write Q equal to X. Though simple, the buffer register suffers from a serious disadvantage. What is the disadvantage? We cannot hold the input bits until we are ready to store them. The moment the positive edge of the clock pulse hits the flip-flops, the input bits are transferred to their respective outputs and are stored. Because of this circuit is no longer used. So this is the basic information about a buffer register. Okay. Now we come to controlled buffer register. In figure 2, we have shown a 4-bit controlled buffer register with a clear input. This is the clear pulse and this is the clock pulse. A high clear input resets the flip-flops so that the stored word becomes Q equal to 0, 0, 0, 0. Okay? See that all the D flip-flops are positive age triggered. Okay? All the D flip-flops are positive age triggered. That means when the positive edge of the clock pulse hits the D flip-flops, the input will be transferred to the output. What are the inputs? Inputs are X3, X2, X1, and X0. And all of them will be transferred simultaneously because the same clock pulse hits all the flip-flops. See that each configuration is the same identical. Each one, whether this is, or this one, or this one, or this one. So let us understand one unit at a time. So what is true for this unit is also true for this unit. Okay? So this is the load. This is the voltage line. Okay? And this one is load not. If this is high, this will be low. And when this is low, this will be high. Clear? So consider one unit, this one, the right one. Okay? See, the load may be high or low. We first consider the case when the load is 0. So that load not is 1. Okay? Now, see here. When the load is 0, this comes here. So this is 0. We are considering the first unit of the figure, only the first unit. Okay? So this is 0. That means this input to this AND gate is 0. So this AND gate has two inputs. One is X0 and another is 0. And therefore, this AND gate is inactive. So output of this is 0. So this output of AND gate is the input to the OR gate. This is also 0. Okay? This is Q0. Okay? So Q0 is this, and therefore Q0 is here. Q0 is input to this AND gate. Load not is 1. See here, load not is 1 here. So this goes to this AND gate. And therefore, the two inputs to this AND gate is 1, another is Q0. So this AND gate is active. So output of this AND gate is Q0. This is also the input to the OR gate. So this is here Q0. Of the two inputs to the OR gate, one is 0 and another is Q0. So the output of this AND gate is Q0. Okay? This output of this AND gate is also the input to this OR gate. So of the two inputs to this OR gate, one is 0 and another is Q0. So output of this OR gate is Q0, which becomes input D0 of this flip-flop, D flip-flop. Okay? So when the clock pulse or the positive edge of the clock pulse hit this flip-flop, this will be transferred here. So Q0 is retained. The output of the D flip-flop is retained. There is no change in the output of the D flip-flop. So X0 will not reach the output of the D flip-flop here. Whatever output is here will be retained when the load is 0. So what is true for this unit is also true for this unit, and also true for this unit and this unit. So X3 input, X2 input, X1 input, and X0 input, they will never reach the output of the D flip-flop. Clear? So this is the first case. And we see the another case. When load is 1, so load not will be 0. Load is 1, so load not is 0. Now, see what happens to the in the case of first unit. See here, this is 0, so this input is 0. This input to the AND gate is 0. Okay, this is 0, and therefore this AND gate is inactive. This AND gate is inactive. So output of this AND gate is 0 because one of the inputs of this AND gate is 0. So this is 0 here. What about this input? This is your load is 1. So this input is 1. So the two inputs of this AND gate is one is 1, another is X naught. So this is active now. So therefore output of this AND gate is X naught. So this X naught is input to the your OR gate. So this is X naught. This is 0. So of the two inputs to the OR gate, one is in the 0 state, another is X naught. So output of this OR gate is X naught. Okay. This is input to this D flip flop. So when the positive edge of the clock pulse hits this D flip flop, X naught will be transferred to Q naught. Okay. So what is true for this unit is also true for this unit, and this unit. So when load is 1, load naught is 0, and in that case, when the positive edge of the clock pulse hits the D flip flops, the input X3, X2, X1, and X naught is the output of their respective D flip flops. Okay. So what we have explained is written here. So the output in this case, when the load is 1, the stored 1 becomes Q3, Q2, Q1, Q0 is X3, X2, X1, X naught. When the positive edge of the clock pulse hits the flip flops. Thus, the content of a register can change only when the load is high. To store the X bits, we take load to high, and after a short setup time, return it to low so that the foregoing word is stored indefinitely. So when this word is stored, we again make load low so that the AND gates to which the inputs are applied become inactive, and the foregoing word is stored indefinitely. The X bits can now change without affecting the stored word. We can now change the input X bits without changing the stored word. Okay. So this is all about the buffer register and the control buffer register. What is the difference between the two? In the control buffer register, we can change the output only when we want, only when the load is high. Then only the output will change. When the load is low, even though the positive edge of the clock pulse hits the flip flops, output will not change. So to change the output of the T flip flops, the load must be made high. This is necessary. This is at our will. When we want to change the output, we make load high. We don't want to change it, we make load low. Okay? This facility is not in the buffer register. Clear? So I assume that you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.